parametric equations. Bless you. So suppose that C is defined by parametric equations, x is a function of t, y is a function of t, and t goes between a and b. Okay. Then, the length of one of these segments I'm going to multiply and divide by delta t, but I'm going to divide by delta t under the square root. So we're dividing by delta t squared under the square root sign, and then multiplying by delta t outside of the square root sign. Where did we see something like this before?
Distance? No.
Well, conceptually close, but so last semester for some of you, and prior to that for the rest of you. What?
This is Pythagorean theorem, right?
What?
I was almost thinking Pythagorean theorem.
Well, that's how we got to that point.
Okay,
But
yeah.
yeah. So as delta t goes to 0, we get ds. The ds that we have in our line integral becomes dx dt squared plus dy dt squared dt. So our line integral is now in a form where we can evaluate. It's the integral from a to b with respect to t, the parameter. And then for our function f, we'll replace x and y by x of t and y of t. So everything is in terms of t now. Alright, this is something we can evaluate. It may not be easy because of the square root, but that's how we would set it up. So something like this we did talk about last semester, but without the f here. What?
Looks familiar.
Well, that's good.
Remember what it's called?
Arc length. Yeah. So if f is 1, you're just getting the arc length of this curve. Okay.
Can you explain to me where the delta t came from again?
Oh, so what I'm doing is so if I'm going to describe a curve using the functions of t, then if we go back over here to how I define this segment, now I can define these as the evaluation of our function x of t at
Okay.
consecutive time values. Okay, and the same thing for y.
All right.
But all I'm doing here, so I have this even before I describe
Right.
parametrically, and now I'm just multiplying and dividing by delta t.
So how did they end up on bottom?
So I multiply by delta t out here,
Right.
and then I got to divide by delta t here, but then I take this delta t and I move it under the square root sign. So now inside the
And
square
you
root
can
sign.
do that because they're both squared.
Yes.
Okay.
Yeah, because these are both squared. So yeah, it just moves in like that. Okay. So when you're given a description of a curve, C, and you're given a function to integrate over the curve, you need a parametric description of a curve. You might be given that already. If not, you need to come up with it. And then you can evaluate your function at x of t, y of t, and then you need this factor that comes from the arc length, and that is what you're actually going to integrate. So in the end, it all boils down to a single integral, which I'm sure is refreshing after all the triple integrals that you've been looking at. Okay, So this is how you integrate a function along a curved path. So let's take a look at, all right, got a couple examples of this. So now here, this is for a plane curve where the curve just sits in the xy plane, everything's a function of two variables. For a space curve, it all generalizes in a very straightforward fashion. X, Y, Z. So the line integral of a function over a space curve for which you had parametric equations again. So now you just have dx dt, dy dt, and dz dt. Okay. All right. Oh, dt.
Is that the technical term for like
Oh,
a three-dimensional space
Um,
curve?
I don't know if it's technical, but it seems to work. Yeah, it's just distinguished from curves that are only sitting in the plane. Plane curve definitely is a technical term.
Okay.
Yeah. Okay. I believe space curve is, but I'm not going to be 100% on that.
Alright.
Okay. So let's do one of these. Well, actually, we'll do two of these. So suppose we have a curve, and the function we're going to integrate over a curve is x squared z, and the curve is a line segment from this point, 0, 6, minus 1, to 4, 1, 5. So what we need to do is come up with a parametric representation of this line segment, and then we can put the integral in this form with the functions x of t, y of t, z of t that we get. So to do that, we'll define a vector v to be the difference between these 2 points, 4, 1, 5, minus 0, 6, minus 1. So we're going to get 4, 6, minus 5, 5 plus 1 is 6. And then, so this gives us the direction of the line segment. So now we can write down the parametric equations. X of t is going to be the initial x value, which is 0, plus 4t. So then, when t is equal to 1, we're at the ending x coordinate. So y of t, similar. We get 6 minus 5t. So when we plug in t equals 1, we get 1, which is the ending y coordinate. And finally, z of t is minus 1 plus 6t. And so t runs between 0 and 1. So when t is equal to 0, we're at this point. T is equal to 1, we're at that point. So anytime you gotta work with a line segment, that's one way in which you can parameterize it. It's quite convenient. All right. So, of course, these are linear functions, so computing these derivatives, not much to that. So x prime is equal to 4, y prime is equal to minus 5, z prime is equal to 6. So now, we can